Hey everybody. So today we're going to talk about transport. So really we're talking about semiconductors. We use them first to transport electricity. So we're going to learn about how that happens and the equations we use for it. So the first idea we have to have is the relationship between velocity and current. So let's imagine we have a little slug here, a little volume that has n electrons per cubic centimeter. And they're all moving with some average velocity. So the question is, how much current is being carried here? So the particle flux, if we say, okay, this slug is going to pass through an area over here, we're going to say how much current per unit area is passing, and that's going to be our current density J. So that's I over A. And we can write that in terms of the particle flux, which I'm going to use the symbol gamma for, and then times the electron charge. So the particle flux has to have units of number per centimeter squared per second. And if we look over here, the velocity has units centimeters per second. So if we multiply these two things together, we get our particle flux. And then we can substitute in and get, in the end, that our J is E times V times N. And I'm going to use a subscript N here to denote electron velocity. Now, in semiconductors in general, we do have two types of carriers, which we talked about in the carrier statistics and band structure sections. So we can write a similar equation for holes, and then by combining them, we can arrive at the total current being equal to E times Vn times N plus Vp times P. So we're summing now the currents carried by electrons and holes to get the total current. So unfortunately, we don't have a microscope good enough to actually look at what the velocity of these electrons are. So we have to calculate that some other way. So now we need to go into a discussion of sort of the microscopic processes that happen to the electrons as they move through the semiconductor. Okay, so let's imagine that we have an electron starting from rest inside our semiconductor, and we're going to apply an electric field. So the force that this electron feels is going to be negative E times the E field because of the negative charge of the electron. So our force is actually pointing this way. Now, Newton's law tells us that this force is also has to equal mass times acceleration. And because we're inside the semiconductor, we're going to use the effective mass instead of the bare mass. So what's going to happen here is this electron is going to start to accelerate. So acceleration means a change in velocity. So we can actually plot on this axis here the velocity of the electron as a function of time. So it starts from rest, and its velocity will increase, 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 increase. Now, we know that this can't go on forever, because otherwise we would have infinite current, because we saw last time that the current is proportional to this velocity. So what happens? Well, this electron, remember, is traveling through the crystal lattice, which might contain imperfections, such as missing atoms, let's say. But also, the atoms are in motion all the time. And these thermal vibrations can actually scatter the electron and make it go in a different direction. So our general picture could just be that there's an obstacle here, and our friendly little electron is going along and then scatters off that obstacle. All of the different events, all of these individual collisions are different. So if you average statistically over many possible events, the trajectory after the collision can be in any direction. And so if we look on average, there's an equal probability of being scattered to the left and to the right. And so what we could say then is the velocity along this direction on average after this collision actually goes to 0. So we know that this can't happen because you have this collision. So then on average, the electron starts from rest again and moves another segment in the crystal until it hits another obstacle. So the trajectory of the electron traces out sort of a sawtooth wave. The time between these collisions might be different because these obstacles might be in different places. They're not regularly spaced in the crystal. So sometimes you might reach a smaller velocity, and sometimes you might reach a larger velocity. So we need to figure out how to take a statistical average of all of these collisions and come up with an average velocity. So this is really key to the transport theory. So what we have is that the V average, and this turns out to be called the drift velocity, can be expressed as some average distance traveled over some average time. So the L here is the mean free path, and the tau here is called the momentum scattering time because we changed the particle's momentum at the event of the scattering. So these are average quantities over billions and billions and billions of collisions. So the net result is that we take this triangle wave versus time, and we represent it instead. This is our velocity versus time. We represent it instead by the statistical average V drift, which we assume is constant versus time. So one thing to note here is that we've completely changed the kinematics of the electron. So the first thing we said is for a free electron, we have force equals mass times acceleration. Okay, but if we include the effects of this scattering, what actually happens is we end up with a statement that the force is proportional to the velocity, and this proportionality constant that we introduce is called mu. So this is the expression for the actual individual electrons, and they do actually obey Newton's law, so don't worry, we haven't broken any real rules. But we're replacing this detailed picture with an average, statistically average picture, which gives you this average electron traveling through the crystal. And in this case, that average electron actually does not accelerate. Rather, it moves at a constant velocity all the time when you have an electric field applied. So this is sort of weird. This is actually akin to the physics that would correspond to parachutists jumping out of an airplane and reaching a terminal velocity. The terminal velocity turns out to be the thing that's proportional to force rather than the acceleration. And so in the terminal velocity case, you get that because you have the drag being more significant than the inertial mass. And so we can say then that the movement of this average electron, the net action of all of these collisions introduces a drag force on the electron and thus slows it down and lets it reach this drift velocity. We can then go back and figure out what our mu has to be. So our mu, to make this equation work out, has to be E times tau scattering over m star. And if we insert that back into our transport equations, we can say that J was equal to E times n times velocity, and using that the velocity is related to the force, and the force is related to the E field. So we have E, n, and then mu times E, and the last expression is E n E tau over m star times E. So we can collect terms here, and the final expression is that J equals sigma times E. And this is actually an alternate expression of Ohm's law. So we can see that in the last transformation here, if we substitute I over A for J, and we substitute in sigma, we substitute in a voltage applied over a distance for E, and then rearrange, we can get that I times L over A sigma is equal to voltage. And if we want to recover the traditional form of Ohm's law, we have to collect these terms together and write that R equals rho times L over A, where rho is defined as 1 over sigma. So we've covered Ohm's law actually by looking at the individual scattering events of an electron and then taking a statistical average, which gives us an effective drag force. So this drag force is what turns out to cause the resistivity of a material. So the last expression to write out is that sigma total is going to be the sum of the electrons and holes contributions. So that's going to be E n mu sub n plus E p mu sub p. Okay, so these are some of our fundamental equations for transport. Now we'll look at the two types of driving forces for transport, which result in drift currents and diffusion currents. So now let's look at the mobility itself and how it changes in a semiconductor as a function of doping first. So if you plot the logarithm of n here, and n is going to be your net ionized dopants, per centimeter cubed. So this is actually the sum of Na minus plus Nd plus. And this is important to remember, that both the plus charges and the negative charges that are fixed in the lattice affect how the electron moves. So generally, in a semiconductor, for low doping, the mobility is rather constant. And then at high doping, it falls off to some low value. So for silicon, for example, this upper number is about 1450 in these units of centimeters squared per volt second, and the lower value might be around 100. And this transition region occurs somewhere between 10 to the 15 and 10 to the 19 per centimeter cubed for this total ionized dopant concentration N. And physically what's happening is if you have negative and positive charges randomly embedded in the crystal, the electron has to react to each of those as it tries to travel through the crystal. And so it's scattering off of all these charges and being pushed and deflected from its original path. There are three important mechanisms that limit the mobility. The first we just talked about is ionized impurity scattering. So this has a functional dependence of t to the 3/2 over n. The second is neutral impurity scattering. And this just depends on the number of neutral defects. And this shows up typically only at very defective material and at low temperatures is the only time you'll be able to see it. And then the last is called phonon, or lattice vibration. So this has a functional form of t to the negative 3/2 theoretically. So we can plot a schematic of mobility versus temperature for two different semiconductors. So one that is sort of in the normal range of behavior would go something like this. And these are on log scale. So this is t to the minus 3/2. This is t to the 3/2, corresponding respectively to phonon scattering and ionized impurity scattering. But another piece of semiconductor, which might be contaminated or alloyed, for example, let's imagine that this might represent silicon, and this next one I'll draw will represent silicon germanium, such that you have neutral germanium atoms intermixed in the silicon, but they still end up scattering. You might have a constant but lower mobility as very low temperatures are approached. So these are representative of the typical behavior of semiconductors at low electric fields. And let me highlight that this mobility picture only works when Ohm's law is obeyed. So in this section, we've just looked at how a microscopic picture of scattering inside the semiconductor can lead actually to resistance and resistivity and actually Ohm's law. And in the next section, we're going to look at deviations from that simple first order picture.